Welcome to my presentation, ECMAScript latest and upcoming features. So we'll get to see what's new in JavaScript and what the future brings. Before I do that, I'll also give you a little bit of background. I'll tell you who designs JavaScript and what process they follow when they evolve it. You'll see lots of code, so it'll be a fairly technical talk, but that's the way I do talks. All right. First, the evolution of JavaScript. How is it evolved and who designs it? So, two words you'll often come across in the JavaScript universe. One of them is JavaScript, the other one is ECMAScript. But what is the difference? So on one hand, you have JavaScript, which is the programming language. On the other hand, you have ECMAScript, which is the standard for the language. So whenever you see ECMAScript 6 and so on, it means that you're seeing versions of the language. And ECMA is simply the standards organization that hosts ECMAScript. And within ECMAScript, there is the so-called ominously sounding TC39, and that's short for ECMA Technical Committee 39. They are the committee that evolves JavaScript. And the members of TC39 are, strictly speaking, companies. So all major browser vendors are in there. Twitter is, Facebook is, Netflix is, a lot of other companies are. And that is quite amazing because all of these companies are usually fierce competitors, but they're working together for the good of the language. So that's really nice. And TC39 holds meetings. So there's one every 2 months. And they're attended by delegates that are sent by the member companies. And they're also attended by invited experts, so people outside of TC39 that have expertise that helps with JavaScript. So this is a list of the companies that are part of TC39. So you can see lots of companies, Adobe, eBay, Google, Hewlett-Packard, lots of other companies. All right. Oh, one real quick note. You can actually look at the slides right now, which may be helpful because then you can go back if you've missed a slide and want to look at it longer. So if you go to this URL, you can actually look at the slides. So that may be helpful. So this is a timeline of the various ECMAScript versions. So everything started in 1997, so quite a long time ago. That's when that was the first time that JavaScript was actually standardized. Before that, it wasn't. ECMAScript 2 came out in 1998, had a few minor edits. ECMAScript 3 was a major version, a major upgrade. It added many features that are now considered core features. So before ECMAScript 3, you didn't have regular expressions. You didn't, string handling improved a lot. There were new control statements. So before ES3, there was no do while and no switch statement. And before ECMAScript 3, there was no exception handling. And that explains why JavaScript so often fails silently without throwing an exception. Next came ECMAScript 4. And that would have become a huge version, a totally different language. So it was completely different than ES3, a monster with lots of features. So it was good that it was abandoned after a long time, that they tried to make it happen. It was abandoned in 2008. Next came ECMAScript 5. That was a minor upgrade of ECMAScript 3. It brought a few minor improvements. It added stuff to the standard library and had the so-called strict mode. And next, in 2011, came ECMAScript 5.1. And again, minor edits. And finally, in June 2015, 2016, we got ES6. And that was really a big upgrade with lots of new stuff in it. But just a quick question. Who of you has already worked with ECMAScript 6? Please raise your hand. So, all right, awesome. It's almost everyone. Okay. And the problem with a release that is as large as ES6 is that features that are ready sooner have to wait until the whole monolithic release is finished. That's a bit of a problem. But on the other hand, features that are not ready yet are under a lot of pressure to get finished. So, because if they don't get finished in time, they would have to wait several years until you can actually use them. And due to that, these larger features, these features that are not ready yet, tend to delay the release. So I think ES6 was delayed by about 2 years or something. Therefore, in order to kind of fix this problem, TC39 introduced a process for designing JavaScript. And with the process, features are managed individually. So you don't have this huge monolith, but you have individual smaller features. And each feature is managed via a proposal that goes through stages. And the first stage is 0, it's a straw man when you just start out. And when it's finished, it's at stage 4. And that allows you to introduce features gradually. So if they're at an earlier stage, you can already play with a feature. And once a year, there's a release. So every year, there's a new ECMAScript version now. But only features that are ready are added to it. So that keeps everyone relaxed and keeps the yearly releases relatively small, especially if you compare them to ES6. All right, let's quickly go through the stages. Stage 0 is the so-called strawman. It's a first very small sketch. It can be submitted by anyone who signs a few contracts. And what's required for this sketch to reach stage 0 is that TC39 looks at it during a meeting and says, this is ready for stage 0, and then it's at stage 0. Stage 1, things advance further. Now the kind of rough sketch is now an actual proposal, and that means that TC39 is willing to help with the feature. Before it can reach stage 1, there has to be a designated so-called champion. And the champion has to be a member of TC39, and he kind of accompanies and helps with designing the feature. And the language or the content of the proposal is still relatively informal. So you have human language, prose, in which it is written. And you can already have like first implementations, kind of experiments. And at this stage, major changes are still. All right, okay, excellent. So major changes are still expected at this stage. When it comes to stage 2, we're now getting to a real draft of what will end up in the spec, and you have to use the kind of weird spec language now. And it means that if a proposal reaches stage 2, eventual standardization is likely. So you can already kind of bet on this feature. And before it can reach stage 2, there have to be 2 experimental implementations. And that is brilliant because these proposals move from something that's theoretical into something that you can actually play with. And that obviously provides feedback to the people who work on the feature. So that's a really nice feedback loop then. At this point, things are already relatively stable and only incremental changes are expected. When you get to stage 3, the proposal is mostly finished. Now all that's needed is more feedback from implementers, from people who implement the features of the feature in JavaScript engines, and from people who actually use the features, so that will be programmers. And what you have to have now is 2 spec compliant implementations. So again, something that you can use in the wild and that is compliant with the spec. At this point, the only changes that are still going to happen are in reaction to something critical that was encountered while using the feature. At stage 4, it's finished, and the one prerequisite for this stage is that there now have to be acceptance tests. So every feature in JavaScript has a test suite that tests if the feature works, and that kind of guarantees that all the different JavaScript engines that they work the same, and the JavaScript engines are remarkably compatible, and that's due to this test suite here. And once the proposal has reached stage 4, well, as I said, it's finished, and the proposal will be integrated into the whole spec text as soon as possible. And when the spec is ratified, then the feature is actually a standard feature. But there's an interesting change in how we now think or should think about JavaScript features. So previously, it was all about ECMAScript versions. And with the new TC39 process, it's more about features and the stages that they're at. Because as soon as a feature reaches stage 3, it's already pretty reliable and won't change much. So, and the thing is, if you think in versions, and you say, well, this feature is an ES7 feature, for example, that's as some people who write about it on the web do, then it's the eventual ECMAScript version that feature ends up in may change, or it may be dropped. So you have object observe that was already at stage 2 and was dropped. So thinking in stages is better. And I start looking at new features once they reach stage 3, because for stage 3, it's before that, it's just not worth looking at it because things change too much. But at stage 3, you can start to rely on it. There are 4, when it comes to features, there are 4 areas that we're going to look at. So on one hand, there's more functionality for the standard library, and that includes object entries, Array.prototype.includes. Then there is new syntax. So you have the exponentiation operator, which is a completely new feature. And you have more support for asynchronous code. There are async functions and async iteration. And you have support for parallelism. So you have SymD.js and SharedArrayBuffers. So that's very exciting. And more features that don't neatly fit into categories sometimes. All right. So 2016 is a tiny feature and is a tiny release. It only has 2 features. So one feature is Array.prototype.includes. The other one is the exponentiation operator. So not very exciting features. We'll look at them in a second. But it also shows that that the whole TC39 process works, because ES6 took a very long time for programmers to get used to, and for implementers to actually implement all that stuff that was in ES6. So having a tiny release in ES 2016 is good. Array.prototype.includes is a method for arrays, and you can check whether the parameter is in the array. So here we're checking whether A is in the array, and that is true, as you can see. And D is not in the array, which is why false is returned. What is kind of nice about Array.prototype.includes is that it can detect nan. So nan is the only value that is not equal to itself, which is strange. But includes finds it. On the other hand, index of does not find it. Then you have the exponentiation operator, which is not a big deal. It's just nice syntax from math.pow, so you can square stuff. And you also have an assignment operator that lets you exponentiate stuff. So it changes num in this case. It squares it. And now we're looking at the future. Several features are already definitely part of ES 2017. And the nicest one is async functions. I'm really, really happy about that one. I'm really looking forward to that one because it's just so useful whenever you write asynchronous code. So right now, promises are slowly becoming the dominant way of doing asynchronous programming. But the problem is, if you switch from synchronous code to asynchronous code that is based on promises, then the coding style totally changes. So you have these method chains here, and it's totally different of any kind of code you would write synchronously. What we have is two calls that return promises. So fetch returns a promise, and in order to get to the content that is delivered via the promise, we need the method then with a callback, and this is the actual content delivered by the promise. And then we make another asynchronous call to a method that returns a promise. Again, we access it here. And for error handling, we need, we need the catch method. So everything is based on methods. On the other hand, if you use an async function, this down here is an async function, then the code looks a lot more synchronous. So switching between the two styles is very simple now, and the code looks nicer, I find. So note the async in front of it. This is an asynchronous function declaration. And now we're making the exact same function call. So async functions work with anything that returns a promise, which is cool, because there's already so much stuff out there that does. And all you need is this await operator that's only available inside async functions. And what the operator does is it puts the function to sleep and then waits until the promise is settled. And once the promise is settled, it wakes the function up again. And the result of this operator is the value delivered by the promise. So, and then you can assign it in totally synchronous looking code. And if any promises are rejected, await produces an exception. So you can use try catch as you would in synchronous code. And there's several variants of async functions. You have an async function declaration. You have an async function expression. You have even an async arrow function is there. And it looks kind of nice because, you don't have a lot of keywords in arrow functions, and now there's a keyword. So I think it looks kind of good. And finally, you also have async method definitions. All right, let's look relatively quickly at how async functions actually do their thing. And here you have an async function. And the result of an async function is also always a promise. And if you want to fulfill that promise, you simply return a value. And after that, you can use other async functions to work with the result, or you can just use the typical directly promise-based style. And here you see that we use the then method to access what's been returned by async func. And that's 1, 2, 3. If, on the other hand, the async functions wants to reject the promise it produces, then all it needs to do is throw an exception. And again, the catch callback, that's typical promise stuff, allows you to access the rejection value, which is the exception thrown here. If, on the other hand, you want to handle rejected promises that someone else returns to you, you use the await operator and then try catch, as we've already seen. And again, this is a normal promise. So a lot of code that's out there, a lot of libraries that are out there work even more beautifully with async functions. Async functions are already in Node.js. So if you download the latest Node.js version, all you need to do is, so it's still behind a flag. So if you activate this command line option, then you can use them in the REPL and in your Node.js code. Next is a relatively small addition that provides more functionality for the standard library. We already have object.keys. Now we additionally have object.entries. And this method returns all the properties of an object as key value pairs, as you can see down here. So here we have an object. It has two properties, property 1 and property 2, and then it returns those in an array as key value pairs. And what that gives you is a nice way of iterating over objects. So here you can see that's the for of loop from ECMAScript 6. And if you combine it with the structuring, you can fill in K and V nicely. And well, as I said, it's a really nice way of iterating over properties that you now have. Object values just completes what's been started with object.keys and object.entries. It returns all the property values, so it's not that useful. String padding is nice if you do any kind of shell scripting with Node.js, and it just pads it. You can either pad at the front or you can pad at the end. You can specify how long the padded string should become, and you can specify the string with which things should be padded. Then you have object get own property descriptors. That is more kind of an advanced feature. And what it gives you is, if you provide it with an object, it returns so-called object descriptors. And those provide detailed information about the properties. So here you can say, here you can see that the property whose key is the symbol is writable, and it's enumerable and configurable, and the value is 1 to 3. On the other hand, you can see that bar has a getter, but not a setter, and so on. And why is this useful, apart from the weird people who work with object descriptors, with property descriptors? And it's useful whenever you want to have precise copies of properties. So object.assign is limited. For example, it cannot transfer getters and setters. And it also doesn't transfer whether or not a property is writable. And with object.getOwnProperty descriptors, you can finally do that. So if you use object.define properties with getOwnProperty descriptors, you copy properties very precisely from the source to the target. If you use object.create, you get a very faithful clone. And even the prototype now is the same as the prototype of the original. The next feature is also minor. As a bit of background, trailing commas are allowed in object literals and in arrays. And that is useful for two reasons. Reason number one, rearranging items is simpler, as anyone can attest who has worked with JSON. Because package JSON, anyone? And then if you rearrange items and you remove commas and add commas, so it helps there. The other thing is if you work with version control systems and all you want to do is add a single line, then the version control system says, well, 2 lines changed. This line has changed too because now there's a comma at the end. And version control systems now then say, well, 2 lines have changed when actually you've only added a single line. So with trailing commas, that kind of problem doesn't happen. That's why it's kind of nice. It's not that big a deal that you can use trailing commas in parameter definitions and in function calls. So here's a trailing comma, and that's okay now with the proposal. And there's another trailing comma down here. Stage 3 proposals. So that's now really the future. These may or may not be in ES 2017. So that's a definite look into the future. Import is nice because at the moment, if you use ES6 modules, everything is fixed. So you need to decide at compile time what the name of the module is. You have no flexibility. On the other hand, with import, which is used like a function, you can specify anything, and this string can be computed at runtime. And it's promise-based once again. So it returns a promise, and once the promise is fulfilled, you have some module, and you can work with the module down here. So why is that useful? The use cases are, you can do code splitting, so you can load parts of your program on demand. It also lets you conditionally load modules. As you can see here, if the condition is true, only then do you import it. And you can compute the module specifiers. Another relatively small feature is the REST operator for properties. Right now, we already have the REST operator for parameters and for array literals. And this proposal brings this operator to object literals. So here we have an example. It's a destructuring feature. You have the object obj. And what we do is we extract foo. That's something that we're directly interested in. And then we extract all the remaining properties into REST. So afterwards, you end up with foo being 1 and REST being this object with the remaining 2 properties of obj. And that lets you, if you use object destructuring for named parameters, you can say that the 2 parameters I'm mainly interested in are param1 and param2, but I also want the remaining parameters, named parameters, that are passed to me. Then there is the reverse version, and that's the spread operator. Spread is already relatively popular in ES6 for array literals. Now you can use it in object literals. And so here you have an example. This is an object, and if you apply the spread operator to the object, you insert all of its properties into the object created by the object literal, and then you add one additional property that's baz. So you end up with foo and bar coming from object, and with baz coming from here. What are the use cases? So again, a bit similar to the spread operator for in array literals, you can clone something. So here, clone 1 is a clone of the object. You can also merge objects. So the merged object has all the properties of object 1, and then all the properties of object 2, and if they're conflicting, object 2 wins. Then you can also use it to fill in defaults. So here we have an object with defaults, and the user data only overwrites those when they're provided by the user. It also lets you non-destructively update a property. So I want foo to have a different value, but I don't want to change object down here. So what I do is I make a copy of object, and then I change foo. So I have a copy, and only foo is changed. Then there is global, and so far, if you want to access the global object in JavaScript, you have several options, and none of the options is truly cross-platform. So in browsers, you normally use window, except when you're in a worker, then you only have self, and that also works in the main thread. In Node.js, you only can use global. And now, thanks to the proposal, global, which also incidentally is a global variable, now works everywhere. And that is really cool. Well, if you need it. It's with modules, you need it less and less. You need less and less access to the global object. Now we're getting to better support for concurrency and parallelism in JavaScript. Let's start with a brief history of what happened so far. And things started with a single main thread and asynchronicity via callbacks. Then came web workers, which were real threads, and it's a really nice feature. But things were, and that's good that they're very limited, because they're also very safe. So in other programming languages, such as Java, you can shoot yourself in the foot with all the multi-threading features. With JavaScript, you're always quite safe because nothing is ever shared, and there are no locking mechanisms. So with web workers, originally you could only send strings that were copied. Later came so-called structured cloning, so you could send structured data. Again, if you sent data from one worker to another one, the receiver receives a copy, so nothing is shared. With transferables, you had something that was higher performance, because if you need to copy stuff, whenever you want to send it from one worker to another, you can. It's kind of obvious that takes time, and this was a faster option. And now the data was simply moved. So the sender, after sending an object to another worker, loses access afterwards. So again, nothing is shared, and again, that's a good thing, because you're safe as a programmer. But on the other hand, you want more than that. For more parallelism, you want a tighter interlocking between the threads. And there was one failed experiment that was called PJS, which is an abbreviation for parallel.js. And the codename was River Trail. It was supported by Intel, among others. Was kind of an experimental implementation was in Firefox. And it provided high-level support for data parallelism. So you had parallel versions, data parallel versions of map, filter, and reduce. And that never gained traction. It never became popular. And it's really, really hard to find good high-level abstractions for parallelism. That's a difficult thing. So the solution for JavaScript going forward is to provide low-level primitives. And those are relatively easy to design. And then library authors can build on these primitives and write something that works nicely on a higher level. And this is kind of the idea of extend the web forward and the manifesto for the extensible web. So SharedArrayBuffers are a primitive building block And now you can actually share data between workers. And you can also do locks. But as a consequence, you can't simply read from or write to and directly or indirectly to a shared array buffer. You need to use so-called atomic operations. And here's a look at what that is like. So here we're creating a shared array buffer with and size it appropriately, so with 10 entries. And then we create a typed array around it. And the shared array buffer is the backing memory of this typed array. And then we send it to another worker via post message. And here it's not copied. The shared array buffer is actually shared. So they have access to the same memory, both workers. And here I store something, and down here I use, so there is this global object that's called atomics. I store something in the typed array at index 0, and then in another worker, I use atomics to load something. And these atomics things are basically like transactions in a database. And that's because when it comes to shared memory, you can have some really weird effects. So modern compilers and even modern processors can rearrange the writes. So the writer up here would, if it didn't use atomics, could write them in a totally different order than you would expect. You also may see partial results. So you may read something down here, and you get a partial result. So you get maybe 1 byte or something, and the remaining bytes are not yet written. So again, this transaction-like mechanism, atomics, that takes care of that. Well, at a cost, but that's what shared memory is like. And these are all the operations. So you have ways of loading and storing and exchanging and so on. You can do simple, very simple arithmetic. A few Boolean operations are available as well. And this helps with doing locks and similar stuff. So here you wait, and check for lock freeness. So that'll be brilliant because going forward we can experiment with what works for multi-threading, and it's also very nice if you compile, say, C++ to JavaScript, because now you can also compile multi-threaded C++ code to JavaScript. SIMD is another feature for parallelism that comes to JavaScript soon. And the idea behind SIMD is that normally if you work in JavaScript, you have so-called SysD, and that is single instruction, single data. So per plus operation here, you work with single numbers. And with SIMD, you actually work with vectors of numbers. So here I'm adding 4 numbers at the same time, and I'm getting out a vector of numbers. And as a result, you get tremendous speed up to 4 times. And in an experiment done by Intel, they even had a speed up that was more 4 times. And they're still investigating why that happens, but that's probably because the shape of the code changes if you support SIMD. So SIMD.js is the proposal to bring SIMD support to JavaScript. One example target are Intel's SSE operations, and there's SIMD right in there. So you write JavaScript, and you can target that instruction set. And the way SIMD.js works is the operands are now vectors of either Booleans, ints, or floats. So here you have 8-bit Booleans, and this is a vector that has 16 of them. This is a vector that has 4 32-bit floats, and this is a vector that has 4 32-bit unsigned integers. And these are some of the operations. So here you have more than you had with atomics. You have several. You have square root, absolute, the negation, and so on. So typical floating point stuff. And the code for actually using it looks like this. So here you're using, this is a factory function. You create one vector with 4 entries, and that is put it into A. Then you create another vector, and then C is the result of adding A and B. And the SIMD.js data types are always 128 bits that could evolve in the future, and support for more bits could be added, but that's it for now. And you can see that you have 8-bit booleans 16 times because those fit into the 128 bits. 16-bit booleans, you have all kinds of signed integers ranging from 16 to 32 bits. From 8 to 32 bits. You have unsigned integers, and you have floating point numbers. And, well, again, this is a feature that you probably won't ever use yourself, but for libraries that do a lot of number crunching, say video decoding, it's absolutely brilliant to have, because you get a lot of everything gets a lot faster. And another minor feature is function prototype to string revision. So with this feature, functions are guaranteed to return source code as much as possible if you invoke toString on them. That was completely optional in the past. And there's a standardized placeholder when toString can't return code, for example, if you have a native function. Template literal revision, again, mainly interesting to people who work with tagged template literals. So you will profit from this if you use libraries or if you're writing libraries. And very briefly, the problem at the moment is, all right, is it coming back? Yes. The problem at the moment is that if you do a \u, a \x, or a backslash plus a digit, then you are not free with regard what follows after that. And that limits you, because with tagged template literals, they're really cool ECMAScript 6 features, because they allow you to embed small languages into JavaScript. So here and all I need to do is implement a function. So here you have support for LaTeX, but you can't write it like this because there's an N after a U, and that's not allowed. And here you have a Windows path, and again you have \u, \x, and that's not okay. And all that the proposal proposes is to change that, and now it's legal. Another, and this is a relatively large feature, is so-called asynchronous iteration. ES6 brought us synchronous iteration. So you have the for of loop, and if you apply it to something that's returned by a function, then you can only do things synchronously. And that's a problem, because if you read from something, especially if it's a stream, then you can't do that synchronously. That's why this proposal is about introducing an asynchronous way of iteration, and that asynchronous way of iterating over stuff is supported by for await, a new kind of loop, which works inside async functions and async generators, which are a new feature that is part of the whole proposal. And all right, so this is a quick example of an asynchronous generator. So here I'm having an existing async iterable, and I'm iterating over it and producing a new async iterable. And well, that's kind of nice if you want to connect streams. And I'm a bit skeptical because it's a relatively complex proposal. It adds yet another kind of function. And my feeling is that, and I may be wrong, that communicating sequential processes are a simpler feature, and these are just a library, and they work with async functions and connections between the so kind of queues. So that's really nice. You should take a look. So if you want to try out any of the new features, go to the Babel website. They have a REPL, and you can tell them what features you want to use. So here you have the latest features that are stage 4 or later. You can also say, please give me everything that's at stage 3. And then you can type the new stuff in here, and you see what it compiles to. And if you log something, you see it down in the bottom right corner. All right, very brief summary. We looked at 4 major areas in new features and upcoming features. So there was more stuff for the standard library. There was new syntax, support for asynchronous code, and support for parallelism, and a few other things. That's it from me. Спасибо.